Today we're talking about bit strings and bit masks. And in the conventional sense, bit masks are something you apply to a bit string. You probably get a bit string from some data source, like a database or a communication link or something like that. And it's a very dense form of passing information where every bit has some significance. And when you apply a bit mask to a bit string, you do that to get information about specific bits or to change the bit string in some desired way. And in order to understand this, you really have to understand the meaning of each bit. Like the first bit is going to be a 1, second bit is going to be a 2, third bit is going to be a 4, fourth bit is going to be an 8, and so on. And this has to do with the power series expansion nature of number systems, which I describe in great detail in video 143, hex dump, as I mentioned in the previous video. And what the bitwise operations are is, the first one is AND, which is a single ampersand. Not to be confused with two ampersands together, which is a logical AND you use in an if statement. And the AND basically says if the bit in the bit string is 1 and the bit in the bit map is 1, you get a 1. But if the bit in the bit string is 0 and the bit in the bit map is 1, you get a 0. And if they're both zeros, you get a 0. So what this is essentially good at is turning bits off, really, because if the bit map is 0 and the bit map or the bit mask is 0 and the bit string is 1, you're going to turn that bit off. So you can use the AND to look at specific subfields within the bit string, including just a subfield of 1 bit. You can AND a bit mask of the 1 bit with the bit string, and if you get the same value as the bit mask, then that bit is on, and you can say this is true. Whatever information is meant by this bit is true. And the OR, if 1 is in the string and 1 in the mask, you get a 1. If there's a 0 in the string and a 1 in the mask, you get a 1. And if they're both 0, you get a 0. So OR is sort of the reverse of AND, in that it's going to turn bits on. Anything that's a 1 in the bit mask is going to become a 1 in the result. So regardless of what it is in the string, it's going to be a 1. The XOR is exclusive OR, and it says if the string and the mask are both 1, you get a 0, because it has to only be one or the other. If you've got a 0 in the string and a 0 and a 1 in the mask, you'll get a 1. And if you have a 1 in the string and a 0 in the mask, you'll also get a 1. It's essentially saying one or the other is 1, but not both. And of course, if they're both 0, you get a 0. The tilde is the flip bits, and it essentially says if you have a tilde 1, you'll get a 0, and if you have a tilde 0, you'll get a 1. So if you want to exactly reverse what the bit string is, you say tilde bit string, and you'll get the exact reverse. If you have 101, you'll get 010, and so on. And this, along with the next two, are what are called unary operators. The ones above are binary operators, where you have 2 parameters of string and a mask. But in the unary operator, you're just operating directly on the string, so you only have 1 parameter. And in the less than, you have a shift left, and you need to specify a number of bit positions. So if you had a 5-bit string that was 11110, and you did a shift left of 3, 3 of these bits would shift off the end into what used to be called all the time a bit bucket, and you just have 1 and it would 0 fill what got shifted. And if you have 1 1 1 1 0 right shifted 2, you'd get 2 zeros for the shifted places, and then you'd get the 1 1 1 from this area here. That's an interesting story about the bit bucket. Back when the computers were the size of gymnasiums, they literally were the size of huge rooms, and you had corridors going through them, and you had people on roller skates, I kid you not, roller skating through the corridors, checking for vacuum tubes that are burned out. And a vacuum tube was about the size of a pickle. And when they found one that was burned out, they'd take it out and replace it with a new vacuum tube. And they'd put it in a bucket they had on their arm. And I heard that was the origin of the term bit bucket. But whether that's apocryphal or not, I don't know. Well, if we look at the program I wrote in order to test this, basically I have all the bitwise operators I talked about in this row here. And the shift left and the shift right, I have a text field to say how many bits to do the shift. And then I have the equivalent of the bit string in the first row, and the equivalent of the bit map in the second row. And then I have a result that shows what the result is of doing the operation of the bit string against the bit map. So if we run this and say I have every other bit set, and do a create bitmap, because the radio button set here, it puts it in the bit string, and we see every other bit set. And then on this one I set only the top 4 bits and clear all the bottom bits, and then do a create bitmap. You'll see we'll have only the top 4 bits set, and then zeros. And if I do an AND of the bit string against the bitmap, you'll see what we get is what was in here is preserved, and what's on the bottom gets zeroed out. So essentially AND is for zeroing out information you're not interested in, so you can just look at the information you are interested in. If we do an OR of these same strings, you'll see anywhere there was a bit set, it's set in the result. And whether they're both set or only set in the string, you still get a 1. So the OR is essentially good for turning bits on. You want to turn on these bits even though they're not set in the original bit string. If we do an XOR of this, you see places where there were 2 1s become a 0, and places where there's only 1 1 become a 1. And if we do a flip bit, or I'd sometimes refer to this as a NOT, you see we get an exact reverse of the original string. You do a tilde of this string, and where it's 1 0 1, it becomes 0 1 0, and so on. And if I create a bitmap, whoops, wrong guy. Want to do this with the string, not the mask. If I create a bit mask that's all 1s, and then I do a shift left of 3, you see I get 3 zeros filled in, and 3 of the 1 bits go off to the left in the bit bucket. And if I do the same thing only the other direction, you see I get 3 zeros filled in on the left, and 3 of the 1s fall into the bit bucket on the right. And the code I wrote in order to implement this, once again, is in a enum with the flags attribute. And the code actually is incredibly simple for doing the ANDing. I just convert the text fields to a byte, and then AND them in the case of the AND, and then display that in the bit result string. And in the case of the OR, it's an identical code except with an OR between the two, and so on. So this code will be out on my website if you want to look at it in more detail. But really the information to understand is what the bitwise operation is, which I hope I've conveyed. Well, I hope you enjoyed this video and learned a lot, and I'd appreciate it if you'd subscribe.